A young engineer, he walks up to me and he says, I don't understand what's so exciting about VARs. I thought, geez. Huh. Young man, they're not only exciting, they're magnetizing. Come on. Okay, it gets better from there. You can't go down. So that's about the end of my levity. Because one of the reasons I wear a tie is it's a very, very serious industry we're in. I mean, we manufacture, develop, design, and provide support for an industry that protects lives. That's what protective relays do. They protect lives, they protect the environment, and they protect assets, ownership. Here you see 3 of those classic examples. You see an arc flash. Now you think perhaps, well, some may think that inverters are exempt from the whole arc flash thing. Not at all. Frankly, the amount of current that a battery inverter can provide is tremendous. And in fact, we had a very close event to one of our employees in India just this last month. We saved his life and our customers' lives by stopping an arc flash event, which would either have injured or killed everyone in the room. So this is why we take protection very seriously. There's nothing cavalier. And those that know me the best, you know, when they say, "How you doing this morning, Scott?" I say, slow, steady, careful. Because an event, any one of those events, is not only possibly a life-ending event, but it is definitely a career-ending event. Okay. So I want to talk for a moment about what us as protection engineers and controls engineers have dealt with for now 100 years. And this is in this case, we'll talk about first conventional sources, and then I'm going to talk about inverters. So first off, a generator has a nameplate, as you see here, and they have for 100 years, and they indicate really beautiful information. Here embedded on the nameplate on the right is the subtransient and transient reactance. Those numbers are used to calculate the fault capacity, how much current, how much juice this generator is going to provide during a fault event. Here's a classical example of how we could calculate from measured data. Here we have measured data. I'm back calculating the transient and subtransient impedances. So very predictable, textbook 101 sort of stuff. The next thing that we are very familiar with in our industry is the prime mover being consistent in its behavior. Here I have 260 kilowatt diesel reciprocating engines that are parallel together. This is in my lab. And controlling them, one in isochronous, one in droop. I can predict their behavior within a few percent with a bar napkin and a pencil. In fact, any one of you can. It's a 1-hour discussion, you'll be experts. Okay, that's wonderful, because now here, and in fact, these behaviors are well documented for the last 100 years. So they're very predictable behavior. All generators, all sizes. Doesn't matter if it's kilowatts or up into the gigawatts. The next thing we know about conventional sources is that they have capability curves. In other words, here we see on this picture a generator capability curve, that's the round shape, and you've got a vertical line. This is the turbine capability curve. Now the green box is a controllable area in which the controller happens to be operating, and the little dot is where it's really at. Now these are critical to understand. We have, as protection engineers and controls engineers, we have to know the reserve margins. We have to know the instantaneous short-term and long-term reserve margins. We also have to know when it's time to trip a generator off. So these are in different ways. They're programmed into relays. Very important that we know where these lines are, because it's about saving lives. The next thing about protection engineering that we must all be aware of is there's 100 plus years of history. Here you see what's called a single line protection diagram. I can go into up to any protection engineer who's skilled in the arts. They don't even have to speak English. They don't. Most of them don't. and I can have a wonderful conversation with a single line diagram like this. This is the universal worldwide standard for how we design protection. And each of these bubbles are called ANSI elements. Each of them has a function. They're defined throughout the standards. They're so old, sometimes the books aren't even pulled out anymore. You can look them all up on the internet. The next point to make is that protection coordination. Here's a very simple example of a miscoordination between an upstream and a downstream protective relay. Here's a miscoordination. Well, there's software which will automatically recoordinate it. Things are so predictable in the power system that we can coordinate thousands and thousands of relays in a few moments using software. This is essential for the success of any deployment of any generator, of any inverter. Anything that goes onto the grid has to be predictable in its behavior so that we can use tools like this, which are established for decades. Now, I want to share with you a little bit about relays are not just protection by any means. The processing power in a feeder relay today, a multifunction feeder relay, is tremendous. We're talking about like more than the world computational power circa 1945. I mean, it's this sort of computational power in the largest relays. So let's talk about what this looks. One of the things we do with relays that you may not be aware of. So first of all, you've got here an example of a microgrid connected to the bulk electric macrogrid. Here's an event where there was a fault on the line between said macro and microgrid, and the relay recorded an event. Okay, this is the top line is the oscillography of current, the bottom of the three-phase oscillography of the voltage, converted to single-phase or to RMS values. Here shown in the blue are the current, the voltage, and the frequency. The three main parameters. What did the relay do in all this movement? So the first thing is it saw that a fault occurred. The subtransient reactance was such that there was a significant burst of current. And after some time, the protective relay said, wait, this is not okay, I'm going to trip. So it closed the contact, it excited a solenoid and a breaker, that breaker began opening. It started extinguishing this current. At such point, the breaker opened, and look what happened. Now the voltage recovered on the microgrid, the current fell, and look what, and then a microgrid controller said, time out, you just had a topology change. The microgrid controller within 16 milliseconds said, okay, you don't have enough generation to support your load, so I'm going to go shed some electrical load. So it shed the load. It made a decision so quickly that, again, we wait for the breaker opening time. That transit time between the microgrid controller acting and the breaker opening is, depending on the breaker, between 2 and 5 cycles. Cycle and a half is about the fastest you can buy today. And voila, you have an unintentional yet seamless islanding event. This is day in, day out the job of a protective relay when configured as a point of common coupling, protection and control. What we have here is most microgrid functions are now established as being done in relays. Okay. Some other things, and I love the discussion the last day and a half because it's really brings to knowledge what you folks don't know and what some of the things I didn't know. I really love hearing about latest in research. And so here's some things you may not know as well. These relays are lovely at doing synchronization. If you have to synchronize one or multiple breakers, you simply put a protective relay at every single point of interconnect, or point of common coupling. Basically one relay per DER, one relay per galvanic contractual isolation point. That relay measures the slip and the voltage angle, and it can dispatch those DERs for you to bring synchronization back in line. This is everyday job for a relay today. Meanwhile, it also does protection, it also does metering, it also does IEEE compliance, et cetera, et cetera. Here's another fun thing that we can do with relays and do regularly. If you've heard of the product that I'm so proud of, which is the SEL PowerMax microgrid controls, this is one of those features we provide to customers throughout the world. And this is what we call an inertial compensated load shedding system. Now, as many fingers and toes as I have aren't enough to count the number of times under frequency relaying has not achieved blackout prevention. We have blackouts, therefore I can guarantee under frequency relaying didn't work. So how do we make under frequency relaying work? Well, what we do is we solve in real time the power equation. Literally the mismatch between the mechanical energy, the fuel into the engine, and the electrical energy out is the power mismatch. And that is characterized by the inertia times the rate of change of frequency, or RPM if it's an engine. And so we can take what is a failing system, an under frequency system which does not work, and we can always make the right decision. We just tell the relay what the inertia is. We tell what all the relays of the inertia of their respective engines are, and they add themselves up and take care of the business. That is the way Microgrid 101 works with the protective relay today. So now we're going to start to transition into inverters. Things are a little different for us as protection and controls engineers. Firstly, some things we know. Governors, fuel governors, whether they be diesel or whether there be a large valve for a steam turbine or possibly a gas turbine, they have about a 1 second time constant. You can do better and you can do worse. We also know that automatic voltage regulators, these are basically DC drives that inject current into the field of a synchronous generator. Okay, they have a response time depending on the L over R time constants, right around a tenth of a second. I'm throwing orders of magnitude out there so that we can get some relevancy. Load shedding, as I showed you before, it makes decisions in approximately 1 power system cycle. So before the AVR can react to a load mismatch, load shedding's made a decision, contacts are closed, breakers are solenoids are already moving. This is important because what you're talking about here is a time scaling that's been designed over 100 years that we must not corrupt, okay? And so it gets better. Now let's talk about distance protection, 21 elements, distance protection, the one that we're gonna talk about in a minute in regards to negative sequence for a moment. These things are wicked fast. Before 1 power system cycle occurs, they've made a decision. So we're talking 2 orders of magnitude in many cases, but faster than the AVR. The AVR hasn't even seen a fault, hasn't even decided to make a change, and the relay's already decided to trip. That is protection 101. This is designed. We all know Nyquist. Well, guess what? Nyquist works for comm systems. It works for control systems, as we well know. It also works for protection systems. There's an order of magnitude here for a reason. When you talk traveling wave protection, we've gone even better. Now we're down to the millisecond. Traveling wave is, we act before the current even moves. Now we look for that reflected phenomena, that pulse of energy coming back from a change in impedance. Beautiful, absolutely gorgeous. But when it comes to inverters, what is the time constant? How does it behave? Is it coordinated? Big question mark for me, because part of what I'm doing here is sharing with you and disclosing with you what our staff has learned. I'm part of a company of well over 1,000 engineers, electrical engineers. The conversations we have are extremely technical, and our engineers not only design the systems, but they are forced to commission them. You don't come home until it works. So when inverters keep our guys in the field for weeks or months or years, yeah, I'm raising my hand here, guys. So let's talk about why. So let's start to dive into this inverter challenge. So first off, it starts with standards we have today. The committees that we are now very carefully beginning to watch and we're a little bit concerned with have created different, and I heard this before, so beautifully and eloquently spoken by several of you, that we have disparate or different requests at different voltage levels. We have transmission system IBRs where the objective is thou shalt hang in there, inverter, until such time that you either destroy yourself or you must absolutely trip off. That's basically the way it works. And I think of that silly little Gangnam Style song when I think of this one. It's like, hang in there, 1547 style, period. Right? So, but seriously, very different objectives given to the same, sometimes the exact same inverters. That's created a problem for the manufacturers as well as us, the protection folks, and the controls. Microgrids, the concept here is actually much more like the bulk electric power system. And this is, hey, we have to, our relay is going to separate us. We're going to, hey, by the way, we're specialists in unintentional islanding, so sorry. That's what we do for a living. But once you unintentionally island, now we're going to tell those inverters what to do so we survive. So the objectives are very different. This is not right. The behavior, by the way, this is the aggregate sum of a lot of learning. And I'm trying to simplify. It's very hard to get all this down in 30 minutes. But I'll say that the inverter behaviors we see are subject to firmware mistakes, to human preference. Here we see a typical battery, a BESS 4-quadrant inverter. This is the way it should be. This is the way it is in the manual. Sometimes we see this, a thin line, only power, no reactive power. Somebody decided that a contract said they weren't allowed to set reactive power control, whoopie-doo. Okay, it's different. I love this one, the Thor hammer. Happens, this was a mistake. This was not just a human preference, this was a darn mistake. So what's the answer? Or I'll send you some new firmware. Time out. I have 300 relays to coordinate with your inverter. You're gonna change something? Oh, wait a minute, that's right. Our labor burden is $2,000 a day. You make one change to the firmware in an inverter, you blew the budget for the entire project because it takes 3 weeks to go change all those relays. Oh, I love this one. It's called the Rorschach splotch. For real, this really happened. I was the guy that, when we start our controls up, first thing we do is we measure the capability curve of an inverter. Yeah, this was awesome. Yeah, he says, oh, I sent you prototype firmware, sorry. Oh, criminy sakes, you already cost me $250,000. What's next? Okay, I can smile because I'm not there. I wasn't smiling then. Okay, here's another great example of some of the challenges we see. Over-complexity. It absolutely smashes reliability. We must make simple, reliable, effective controls and protection schemes because people's lives are at stake. Our businesses are at stake. Our nation is at stake. Everything is at stake. Okay, here's an example of a well-meaning anti-islanding element pushing against a very weak grid. Not that it's not a weak grid, rather that it's a long or a high impedance, a large X thevenin. Basically, it's natural, as I'll show with my tie example, with a large impedance between you and your large power system to have large power angle shifts. And so when these anti-islanding terms push against this very squishy grid, guess what you get? You get false operations. And then what happens then? The inverter says, oh, gee, I think I see an island. I switch to island forming mode, and quickly he trips out because he went over current, because he went out of step. Darn it. Okay, turn those things off. Next thing, and relays know what's going on. The inverter can't know what's going on. There's thousands of inverters in the transmission and distribution system. They will tell you what's going on. Standard answer is turn the features off in an inverter. That's my standard answer. If in doubt, turn it off. You don't need it. Here's another example of very fancy elements causing great trouble for us. Here you have what we wanted to get from a 5 MVA battery inverter, which is a nice droop line. We asked for this. What we got is the bottom. This is a challenge. This is really, now how am I to dispatch something that's reacting to excessively in power to small millihertz level changes? How can I dispatch it? Where's it going to go? It didn't have the basic deadbanding of a fuel governing system circa 1920. Of course, all fixed, it all works, but a challenge. Nonetheless, it costs a lot of time and money. So there's no wonder that inverters are having challenge in the market in some places because they cost too much to commission. Here's one that I love. And I'm protecting all parties. I'm protecting manufacturers, I'm protecting customers. A lot of these are cartoons for everyone's benefit because they not only elaborate the point more simply, but they protect everyone. But what you see here is an inverter. It has a fault, a single phase to ground fault. This is a measured event, by the way. There was a small cessation period where the voltage turned off, and then the voltage recovered. Now, clearly, there's no DQ transformer. There's clearly a single phase control. This is interesting. A bit of a okay, something's happened in the industry. You guys were off moving, and I wasn't aware of it. Okay, got it. I'm with you now. But then another inverter not far away looked like this. geez, there's another single phase to ground fault. But wow, what a different behavior. Now we have very high currents. This is clearly this looks to me like there's a DQ, a positive sequence only type control. You know what I found out about 6 weeks later? They were the same inverter. Same model of inverter, different human settings, different preferences. Timeout, how am I as a protection engineer to know how to protect humans, process, and the environment if they behave like this? Timeout, that's just not cool. The next thing here is I've come to learn, and forgive me, I'm just starting to catch up with some of what you guys are doing and what others are doing in the industry. The power system committees of North America are really starting to pay attention to what's going on. And here's a chart, or rather a oscillography from one of those reports. I don't know where the data comes from, but what it shows is that the red line, which is negative sequence, is very small. In fact, looks to be suppressed. Well, we got that. We know why, because there's a DQ transform, positive sequence control only. But we also know that this negative sequence has become now a research topic for many manufacturers and those in academia. But what I'll also tell you is I don't need very strong I2 to make a good directional element, to make a good protection element. And forgive me, for those of you on the remotely watching and those of you who really know protection, I'm going to do a very simplified version of how a directional element works in a relay. So you can understand, I don't need strong currents, strong and negative sequence. I just need reliable negative sequence voltages and currents. Small, reliable levels of this are plenty. Okay, so here's a scenario I'll explain to you. So you have, again, that microgrid connect with some sort of generation connected to the macrogrid. During normal load import and exports, you have phasor diagrams that look like this, currents related to voltage. I like this sort of diagram because anybody with nearly every engineering education can follow. But we know it's normal load behavior. Those are normal load. We don't want to trip for normal load. We want to trip for abnormal current levels. Now, I've shown you a positive sequence current and voltage. Put this in a negative sequence and we get some advantages. But mind you, the way this works is we just need some level, excuse me, of positive, or in this case, negative sequence voltage and current to calculate the impedance on a continuous basis every few milliseconds. And when the impedance goes in the wrong place, I can make a decision to trip. So here's a great example of where somebody tugged on a thread that some smart guy said, hey, we need negative sequence. Timeout, sure we do, but we don't need to spend all of our time on it. Just give us a little bit. Just give us a little bit. Okay, anybody here aware of the Blue Cut fire and the event that happened down there? Yeah, right? Classic, we're gonna hit that one now. I'm anti-PLL. I'll tell you right now, I need the tie with a little red circle in the line for it. I'm anti-PLL. And what this report has shown to the world is that inverters were off tripping and nobody knew about it. And they were tripping because their phase lock loops were going, basically forcing units out of step. Why is that? Well, it's because phase lock loops are trying to measure something that's not always measurable, and most importantly, not easy to measure during fault conditions. When you have no voltage, how are you going to measure frequency? So here's an example of another problem. We have no two PLLs measure frequency the same way. This is a real challenge. And so this is what's causing so many problems. So let's get rid of those PLLs right now. They're just not okay. Here's another example. Now, I am no inverter expert. I know enough to be very dangerous, okay? But I happen to know my way around an engine, a turbine, and a reciprocating engine, and a generator. I'm going to share with you very briefly what my knowledge and our knowledge has become. We know that you can't put a generator in regards to engines. And I think there's a strong analogy here to be made for how we do inverter control. And it's an argument that lines perfectly with what you've shown me in the last day and a half. So here we know that we can't take an isochronous generator and attach it to the bulk electric grid. We all know why. We also happen to know that steam turbines are primarily power sources. They're not very good at regulating frequency because they got a big steam head to deal with, and the power is either going out the stack or out the electrons. So they're pretty much constant power devices, very similar to the phase lock loop, but they have a little bit of droop behavior. The next thing, when we start to evaluate what sort of droop behavior is best served in a turbine for frequency regulation, we know from absolute certainty over 100 years of experience that a power control loop, such as in a steam turbine facility, with a small frequency measurement for droop, it's a meh. It sort of complies. It's not great. It's a real problem, as we've proven many times. The best is a stiff frequency control loop with a power droop, period. Absolutely no question. Here's an example. Me standing behind bulletproof glass, said turbine, steam turbine takes off, valve full stroke, very bad day. Okay, long story short, why was it? Well, there's a great, every one of these slides, I have multiple papers I could share with you, get you. This is a great paper because what it shows is that as the power system changes in its composition of inverters, PQ loads, motor loads, it says that as the power system was changing, what happened is the control loops inside the steam turbine control, the poles would go the wrong direction because the gains would get very hard. This is called sensitivity. This is one of the first analysis I do when I see a control system problem. And what I did there is evaluate how sensitive the control system is to changes in either impedances, I heard that today and yesterday, or in this case, load composition or compliances. Great papers back to the 1960s that talk about this. Gorgeous stuff, very predictable. This was exactly the problem. We know root cause when we find it. We can turn it on, we can turn it off. So I did, I turned it off by simply taking the steam turbine when it was islanded and converting it into speed control with power droop. Now the analogy to that is grid forming inverter with power droop. So if the turbine industry in the last 100 years has said, hey, that's the way to go for ultimate resiliency, that's probably the first place you ought to look. And I love the fact that you're converging. That to me says, that passes the sniff test. I get it. You're in the right direction. So what are the root causes for all the protection challenges? That's hard to put on one slide. And listening to many of the fellow engineers in my company and engineers throughout the industry and the hundreds of engineers we have commissioning systems today, it comes down to this list, sort of like this laundry list. We have to get through this list. Human preferences are dangerous, if not controlled. The DQ transform, let's see if we can't get rid of that. Not cool. Phase lock loops, gotta go. Human error, you're always gonna have some. This is the most dangerous tool in the substation, right here. Call it fat finger. But there's some things we can do to manage that. And quite frankly, this is where the real risk is to lives, the process, and the environment. Okay, DERs that move faster than protection, that's a big no-no. Give us time to protect the system. Oversensitivity to load composition. I just showed you an example of a steam turbine going unstable, which I personally had to fix and rewrite the code for. And what we know is that we resiliency to me is this: insensitive to changes. You don't want your airplane to flip upside down and crash just because some measurement goes bad. By the way, it's a horrible story. Read about the 737 MAX. It's when overcomplexity causes the demise of human lives. Okay, this is what we're talking about right now. And inconsistent fault currents. You've heard about this before. You've probably heard that you need high fault currents for relays to work. Well, that's just not true. What we need is consistent fault currents, consistent sequence components, predictable behavior. And so what we need is standardization. I'm on a number of committees, a number of our engineers are on committees. One thing I've observed is that paper standards don't carry a lot of weight. Sometimes I tell you what I like is a nameplate. Every time I go up to generator, I walk up to it and I feel very relieved. I have a nameplate that says, here's what its fault current is, here's its rating. I know what to do. Let's get me a nameplate and our engineers a nameplate on every inverter in North America. And if you're so brazen as to change the firmware, well then by God, you're bringing a drill, some rivets, and a new nameplate. Let's save some lives. Any questions?
Just a quick question
Yes, sir.
on basically your coordination. So you mentioned that we have your industry has a very tried and true method of designing coordination. Is it prepared for the extreme bidirectionality that we're trying to push towards as more and more distributed generation is being installed sort of at the fingers of the grid? And so right now the grid, power mostly flows in one direction, right? Comes from major power plants and the transmission system down to the customers. Are we prepared to do protection coordination with strongly bidirectional power flows?
Depends on the skill of the engineer. But by and large, yes. The products, the multi-function protective relays in service today, many of them have directional elements that could be turned on. So it's a matter of adapting the settings. It's not about changing the function of the relay. It's not about creating new protection elements. It's not about changing the relay. It's just go turn on what's already out there. So the answer is yes, for sure.
Thanks for the interesting presentation. So I don't have a question, but I do have a comment about the PLL. So it seems like kind of don't like the PLL, but just want to maybe make some clarification. Right? So you mentioned the group called event.
Yeah.
But I do think I don't know how many of us in the room really look into that problem. So, but personally, I do that work every day, and so I want to make some clarification here. The PLL is, I think, sometimes maybe messed up with the protection. The PLL we know is for the control, and we try to especially for the following order, try to synchronize the grid and to protect the inverter. But the protection of it is a totally different thing. So, so as an example, I did, for G real inverter, so we did all kinds of different simulations or in the real inverter control environment. So we didn't treat that. Although the PL tells us, okay, so you have a very big deviation on the frequency measurement, but that does not mean you need to people to protect. So that's different things. So I just want to add a comment on that. Just not blame all things to the PL. I don't think that's a fair for me. That's not fair.
Be anti-bad PLLs.
Anti-bad PLLs.
Yeah.
Okay. Well, I got to say PLLs are in relays too. And we know that frequency is hard to measure, and during faults it's nearly impossible to measure. So a more robust solution, let's put it this way, a more robust solution would be to have no PLL. And we do know that that has been attributed to be the root cause for a number of unplanned DER islanding events.
Setting up.
Yeah.
Your comment about the fact that the control should not be faster than the protection invites a philosophical question. Should we keep the protection completely separate from the control? Or could some of the protection start to incorporate the devices themselves, which they can be very fast?
I think that's a very valid question, which needs a little looking at. But frankly, the protection that's in the grid today already has a great deal of control. So adding control to a protective relay, yep, that works. Seems like it might work the other way. We have had challenges with that. As you know, there are products out there that do both. That takes some research.
All right, let's stop again. And,